let's look at calculating the volume of a three-dimensional object by slicing it up into pieces. And it's really an instance of a bigger principle that integrals often show up where in situations where the whole of some quantity is the sum of the parts. So you can take some big calculation you want to do, big and complicated and messy, you slice it up into smaller parts, sometimes literal physical pieces, but sometimes slicing it up in time or in other variables, and then you put them back together. Anything where the whole is truly the sum of its parts, and there are cases where that's not true, but anytime where it's true, then an integral is going to be what you're likely to want to calculate. So in this case, that's absolutely true. The volume of a whole object, if I slice that up into any kind of parts, then it's going to be the sum of those little parts. And then the question is, can I do that slicing systematically in a way that I can describe explicitly? And then when you slice it, does it get simpler? So I want to start out with, so what does this mean in terms of the language of integrals? There's a very nice way with very few symbols to indicate that. Ideally, we're going to take our object here and calculate the whole volume. Ideally, we would love to make that sum a sum of infinitesimally small parts, and then somehow get exact answers for those infinitesimally small parts, and then add them up again. Well, that is the integral, and we would indicate that by saying the whole volume is the sum, which is really a limit of sums, it's the integral, of a bunch of infinitesimally small pieces. And those pieces can be rather creatively done, and we're going to look at a few approaches. But very often, this dv should be the volume of a thin slice. And this idea actually goes back way before Newton, way before the sort of official invention of what we see as calculus in modern terms, back to Cavalieri. If you can calculate the volume of a thin slice and add all those slices up, that'd be great. So the idea there would be take a sort of a typical x value here and then slice this, and I'm purposely making it kind of a weird shaped object, but slice it with some infinitesimal width slice dx. And if you happen to be able to calculate, or are given, or know with some other way, the cross-sectional area of this slice at position x, well, that would be really good, because then I've got a three-dimensional slice, but it's really, really thin, and it's got a known cross-sectional area, and the area times the thickness is just going to be the volume. Now, I'm playing very fast and loose with the rigor here, but this is exactly how they would have done it in the starting days of calculus, that an infinitesimally thin slice has an infinitesimal volume, and it's the area of the cross-section times that infinitesimal width. Pretty sketchy, hard to make rigorous in those terms. We usually do it in terms of limits and things like that. But for this video, I think I'm going to not worry about getting an exact answer. We'll definitely come back to exactly this kind of thing, and look at ways where you can get an exact answer. But I'm going to say, well, what if you can only get an approximation? What if you're willing to settle for an approximation? That's going to be approximately a finite sum of a of x times delta x. So instead of this kind of idealized infinitesimal slice, I'm not going to redraw it. Let's say it actually has an actual finite width, but fairly small. And then I still calculate the thickness of the slice times the cross-sectional area. That's going to be the volume of the slice still. Well, approximately, because I'm assuming that this thing is a perfect cylinder. It has perfectly straight edges, even if it could have a funky cross-section. And in particular, I'm assuming the cross-sectional area is the same on this side as it is on the left side, the right-hand side and the left-hand side. And that there's no weird wiggling in between, but of course there is a little bit of weird wiggling in between. So this is approximately going to be the volume of each of those slices, and then I'm going to add those up in some sort of finite sum to get an approximate number for the volume. Well, that is something. So what do I need there? I need somebody to calculate or measure with some sort of technology all those cross-sectional areas. And that's actually not unreasonable. That's the kind of thing that you can actually do in a lot of cases with like medical imaging or industrial imaging or something like that. Or you could actually literally slice the thing up if you prefer destructive methods and just measure the area. Measure the area of each slice. But let's suppose we have that, because it's actually somewhat realistic and it's a great link to things we know how to do. Okay, so now we want to take the sum of these numbers, which in this geometric setting are areas, times the delta x's, which are thicknesses, to get the volume. But you know what? This sum, that's exactly just how you would approximate the integral of this function if nobody told you this was an area function as a function of x. This is just our usual way of approximation to, again, integral a of x dx, which we're still thinking of as the ideal that we can't quite get at because we certainly didn't slice it into infinitesimally small slices, and we in fact sliced it into pretty chunky slices. At this point, the picture is more like, okay, here's, ooh, I should dot that, that's in the back. Here's one slice at like x equals 3. Here's another slice, it's going to have some different area and volume, different cross-section. Here's another one, maybe even funkier. Just drawing all those cross-sections. Here it is at 12, and here it is at 15. And so I've got all these cross-sections at 0, 3, 6, 9, 12, and 15. What am I doing geometrically here? If I'm going to take this data, pretty coarse data, not very finely sampled, and use this to approximate the volume, I'm taking pretty big chunky slices, kind of like this, that are 3 centimeters wide. And let's say this is in square centimeters. So this is in centimeters. And I'm going to want to combine all this data to an approximation of the volume of this object. Still the same idea, though, that if you have something that's basically a cylinder with a weird base, or it could be a circle, but here it's kind of a weird funky shape, and you know the quote height of the cylinder, here it's sideways, and the cross-sectional area, you just multiply area times thickness, or height if you want to use that word, and you get the volume, and just add them all up. So the nice thing is that we don't require any new kind of integral, any new technology. This is a bunch of data for our independent variable, bunch of data points for our independent variable, bunch of values for our function, and we just want to use any of our desired usual approximate integration methods to integrate a of x dx, or in other words, the sum of these a of x delta x's. And since it's tabular data, this is best done not with like a left or right endpoint rule. Those aren't typically going to be very accurate, but with a trapezoid or sometimes something fancier. But with this, there's no point in getting fancier. So we're going to use trapezoid. We've got 1, 2, 3, 4, 5 subintervals. We'll call it T5. And that's going to be, now it's equal spacing. You definitely want to be prepared for non-equal spacing, and we'll do examples of that. But this is good old equal spacing, so we can use the shortcut delta x over 2 times that first cross-sectional area and the last cross-sectional area. You know what? Actually, let me use my preferred one. I've been looking at other people's trapezoid rules, but let's use my preferred one, where I have delta x out here full strength, and a of 0 and a of 15, the first and last, are going to get demoted to half strength, and then the other ones are going to be full strength. Okay, so 3, and then 4 plus 8 over 2, that's going to be 6. Notice it's just the average of those two. And then plus 6 plus 7 plus 10 plus 9, 12, 19, 29, 38. 3 times 38, or 116. Yeah, 114, there we go. And that's, of course, cubic centimeters. If I had left the units in, that's in centimeters, and all these numbers are in square centimeters. So we're getting an approximate volume of 114 cubic centimeters. So we're going to do a lot of this volume stuff. The main points I want to make are the whole is the sum of its parts. We need to figure out how to label the parts systematically, and that's where the difference is going to be with the different methods. And then we're going to get something that's just an integral. We're going to get have an independent variable. We're going to have some function of that, which is going to be our areas of the pieces of the cross-sectional areas, and we're going to integrate it just as we always have.